Well, first of all, I'd like to thank the organizers for the invitation to speak with you today. My name is Kristen Averyt, and I'm from the University of Colorado at Boulder. And what I'm going to be discussing is the power for the water sector across the southwestern United States. So I'm sure we've seen this picture before. What this is just an illustration of the energy-water nexus. Across the U.S., the electricity sector uses or withdraws about 41% of all the water and accounts for that. That is actually more than is withdrawn to support the agricultural industry. On the other hand, the water sector is actually responsible for about 13% averaged across the United States of all the electricity supply. But in the Southwest, and what's really interesting about the U.S. is when you look regionally, you see significant differences relative to the national averages. In the Southwest, a very small fraction of the water is used to generate electricity. On the other hand, a disproportionate amount of the electricity generated and used is actually there to support the water sector. So what I want to focus on today is the energy embedded in our water supplies across the Southwest. This graphic represents, it's one indicator of surface water supply stress across the United States. Where you see shades of red and yellow, these are not places that have no water per se. Rather, this is where water demands are actually being met by overpumping of groundwater, conveyance systems, reservoirs, or there's a heavy reliance on return flows into the system. But of course, conveyance, pumping, et cetera, these are very energy-intensive processes. To give you a perspective on this, in the city of New York, if you live there, the energy intensity of the water systems there is roughly 2,700 kilowatt hours per million gallons. In the Bay Area, where we are today, that number is about 4,000 kilowatt hours per million gallons. That's primarily because of groundwater pumping as well as the conveyance systems that are in place here. And if you live in Southern California, you are using roughly 10 times the amount of energy to support your water supplies relative to somebody that lives in New York. So if one really wants to consider your greenhouse gas footprint and reducing carbon emissions, one should also look at where you live and where you get your water from. So I want to focus, as I mentioned, on the Southwest. This cartoon represents the water delivery systems that are currently in place across this particular part of the country. This is by no means a comprehensive look at all of the large scales of the major water supplies, but these are some of the largest systems that exist. In total, these systems deliver about 12 million acre feet. I'm sorry, I'm from the West, so I speak in acre feet. About 12 million acre foot of water annually. That is, to put that in perspective, that's roughly the flow on the Colorado River, 12 million acre foot of water that's being moved around the West to support towns, cities, as well as agriculture. This equates to almost 300 miles of pipelines, canals, and aqueducts, and it also considers, we have water systems that are moving water over Tehachapi Pass as well as across the Rocky Mountain West. These systems here in black, these are actually net generators of electricity. This is because they're mostly gravity-fed systems. But the ones in blue still account for a large proportion of the energy and the electricity demands across the West. To put this in perspective, this is the energy embedded in these large-scale water systems. The Central Arizona project in Arizona is one of the most energy-intensive water systems in the United States. On average, about 2,500 gigawatt hours are required for every cubic kilometer of water that is actually provided in that particular region. It's also worth noting, considering the energy-water nexus and the role of climate, that the Navajo generating station located on Lake Powell, about 40% of the electricity generated there is used by the Central Arizona project. 90% of the electricity to power that system comes from a coal-fired power plant. Again, this is also not about the energy embedded in the water systems, but also the carbon embedded in those water systems. Of course, we're looking at a future that is potentially drier. It's not just about being drier and perhaps less water, a diminished water supply, but also increased demands. This graphic just shows the potential increase in surface water supply stress across the Southwest just as a consequence of climate change. And this is the long-term trend. This is not looking at drought events or any of those severe events that really pose significant risk to the system. So what is the water sector doing to try to adapt to this future? Of course, it's considering additional infrastructure and additional storage systems. So again, Here is our current infrastructure. These red lines represent the proposed water systems that are potentially coming online in between the next 6 months and the next 20 years. These are all going through, at least are in a NEPA review process at this point. So what my team did is we went through all the NEPA documents, and we also looked at a lot of topographic maps to try and estimate what might be the lower bound on energy demands to support these new water systems. These proposed deliveries, they're an additional almost 5 million acre-foot of water, and that's worth noting. So these are the gross power intensities of the new systems that are potentially coming online. This blue line, that blue line represents the energy intensity, and that's the net energy intensity of the Central Arizona project. So we're looking, we can see here, first of all, there is a challenge. This energy intensity of these new supplies is very significant, particularly when we're looking at how much of our electricity is already going to support the water sector in the West. But it's also an opportunity because there are opportunities to reduce that, to reduce these relative footprints by through gravity-fed systems as well as through investments in renewables. I should point out specifically the Carlsbad desalination plant that's coming online in Southern California. That is the maximum energy intensity. Right now, the folks that are standing up that system believe that they're going to be able to reduce the net energy embedded in the water that's going to be produced there by about half just through investments in renewables as well as new technologies. But as one of my favorite colleagues likes to say, rather than just admiring the problem, we're trying to also do some quantification of some of the issues surrounding the water systems in the West. And led by my colleague David Yates at NCAR, he's been working to integrate two models, the WEEP model and the LEAP model. WEEP is the Water Evaluation and Planning System, and LEAP is its energy counterpart, or electricity counterpart. These models are by no means as sophisticated as a lot of the work that we've already seen presented today, but what is very useful, particularly with respect to WEEP, is that it allows us to incorporate the policy drivers that really define water availability in the West. For those of you not from the West, really, it's not just the physical availability of water that defines how much we can access, it's really about the legal regimes. So that's one of the reasons that we've been playing around with these two systems. So one of the things that we have been tinkering with is we've been looking at what the system would do in the Southwest under a 10-year prolonged drought. Don't have enough time to go into the details, but suffice it to say, I'm going to show you some of the results of a quote-unquote normal climate regime versus a 10-year historic drought. This graphic on the top left represents the total storage on Lakes Meade and Lake Powell over in two different scenarios. The blue represents our normal climate, and the orange represents a 10-year prolonged drought. What's interesting here is just because of the demands that are placed on the system, we're looking at significant drawdowns on both Lake Meade and Lake Powell in the future. That's important because these reservoirs represent 5 to 10 times the store 5 to 10 times the flows or the annual flows on the Colorado River. What's also interesting, even under normal conditions, just because of the demands that we have in the system now, we don't see recovery of these systems until about 8 years into quote-unquote a normal situation. What does this mean for power generation? West-wide power generation. What's very interesting here is that during our 10-year drought, the power generation absolutely tanks, and that's not just because of diminished hydropower generation, but also because of the availability of thermoelectric power and increased demands for air conditioning on the system. It's also worth looking specifically at California and CO2 emissions. Again, here red is our drought, blue is our normal conditions, and what we see is that after 8 years of a drought, the power for water signal really emerges. And that's because, and it emerges kind of late because we were assuming conservation and efficiency standards would be implemented. But one of the really important stories is about the CO2 emissions. When we see under a drought scenario, because of additional pumping of groundwater and additional energy demands on the system for pumping as well as conveyance, we see significant increases in our CO2 emissions in the state of California. Unfortunately, a lot of this modeling, we did this quite a while ago, and a lot of what we're seeing is coming to fruition right now in the state. The current drought is expected to continue through 2015, despite the atmospheric river or the Pineapple Express event that just occurred. We have already seen significant declines in the hydropower generation in the state. And fortunately, thus far, both solar, wind, and natural gas have been able to make up that difference so that California was able to actually meet its renewable portfolio standards. That said, if the drought continues, there may be challenges in meeting those kind of carbon emissions. So one of the key messages and one of the things that my team really likes to think about, I shouldn't say likes to think about, but that we really try and consider is how sectoral adaptations relative to the water sector can really compromise efforts towards carbon mitigation technologies. And we're really looking at what's happening in California to try and quantify what those issues around the Nexus might be in the future. And I'm out of time, so thanks. Any questions?
Please.
All right, thanks.
No, you can't.
Just kidding, Vince. Yes.
So what's the long-term implication if the compensation is for more groundwater pumping on groundwater supplies?
So I'm glad you asked that question. This is something that we are also working on in terms of looking at the relative drawdown of those of the groundwater supplies, particularly in the Central Valley. Right now, we're already seeing the recharge rates are not meeting the pumping demands. In fact, on that last slide, I didn't talk about this in detail, but the revenue loss to the agriculture industry has been $1.5 billion related to the drought. And a third of that is because of increased energy, the cost of energy required to pump the groundwater from even deeper depths. Deeper depths, yeah. All right, thank you.